Hi. Exam 2 coming up tomorrow. I'm not excited, no.
So then just make it one question.
One question, that's...
No.
That was a excellent idea. One question.
Do you find that question for Calc 2 that has all of the...
methods of integration in it? I don't think I can pull it out here, but So, welcome to Exam 2 review, which is on Chapter 15. So, Chapter 15. If you would like anything else included, just let me know. About 10 questions. Again, 100 points. This one has higher stakes than the previous exam because this one is valued at 13 or 14%. Previous one was like 10 or something. So higher stakes. And the format is going to be the same like last time. There will be calculation questions, and this time around we're finally going to have a word problem for Lagrange, right? So there's that. Overall better exam than the last time. After that we will have the lecture to talk more about 16.2 and then 16.3. So there will be a lesson after the exam. The exam will contain definition of a function, which is given in I think 15.1, and then figuring out computing level curves, which is when you set z equal to a number, and then the shapes. I might do the multiple choice to match the shape to the equation. Limits. There are, I think, 3 flavors that we worry about. Basic, just plug in. And then we have boundary, when you do the algebra, mainly factoring or rationalizing or something simple. And then we have limit does not exist. 2 paths, right? 2 paths where they give you different value of the limit and you claim the limit doesn't exist. Continuity. We have the 3 rules. That's the at the point. And then all of the, maybe I should have used the arrows to be consistent. So 3 rules, which is for at the point, and then global, that's the theorem. Partial derivatives. I'm not sure if there is going to be a standalone question for partial derivatives because everything after this is using a whole bunch of stuff for partial derivatives. So partial derivatives are part of every section from 15.5 through 15.8, like those 4 sections, they all have partial derivatives in them. But partial derivatives, I'll just say fx, fy, fz, right? That's what we have. Chain rule. Draw the tree plus get equations, get equation. And second one, compute. So an obnoxious problem, right, to just set up and then a cheap problem with, you know, 1 or 2 things to compute very quickly. So possibly 2 problems on chain rule. Directional derivative. Why am I changing the color to red? What am I going to write next to directional derivative? Maybe I shouldn't write it next to this.
Oh, something about a unit vector.
Yes, I'm gonna write unit vector, yes. Unit vector, because that's where your grade goes to die. Make sure you're using unit vector, not, because most likely I will not be giving you unit vector, you get one. Gradient. Again, probably not a standalone problem on gradient, because gradient is the part of Lagrange, right? And it's the part of the directional derivative, so you do have gradient featured already. Tangent plane, which is linear approximation. Differentials, that was then the delta z was approximated by dz, which was equal to, and then you have your f of x, blah blah blah. Min max. So min max, how about min max saddle? The formula needs to be known. Now clearly there has to be something that it's fast and quick to compute, otherwise, because we are not trying to sleep here. And then finally Lagrange. Lagrange multipliers, where you have your del f equals to lambda del g. I am going to probably use 2-variable Lagrange. If I'm using 3-variable Lagrange, then it's probably going to exploit the symmetry, or when you write all of those 4 equations, one of the equations is immediately going to spit out the value. I'm not going to create a 3-variable Lagrange plus lambda, so equation 4 unknown Lagrange that will take an hour to solve. So if you are taking forever on Lagrange, you are doing something wrong. We need to somehow squeeze all of this into an hour and 20 exam. So that's what we have. Questions, concerns, suggestions to add any material? Someone suggested, can we have Pythagorean theorem in sure, I'll work it into Lagrange somehow.
Some simple addition, individual problems.
Simple addition, individual.
Like problem 11, 2 plus 2.
Extra credit.
100 points extra.
Yeah.
As a
Always. This is what I always do when
You
a
can leave
student
one blank
who's running a negative 7 average says, "Can I have extra credit?" Hold on, you haven't done the credit yet. You want extra? What do you mean extra credit?
I'm good, I'm gonna make it.
Nice. Any suggestions to add any material? No? All right. Any problems that you guys would like to ask, work on?
Just like a quick clarification thing. Directional derivative is where you take the gradient and then multiply it by a unit vector in a certain direction.
Dot product with a unit vector, yes.
Okay.
Directional derivative is fx, fy times u1, u2 in a dot product.
Okay.
and it will give you the slope of the tangent line in that direction on the surface, which is yes. And it has to be unit vector so it doesn't mess up the magnitude of your derivative.
The directional derivative is the partial derivative of x, partial derivative of y, dot product, unit vector,
U1, U2.
u1.
So I'm going to, in class I gave you the unit vector 3, 4. I mean, I gave you the vector u, 3, 4, but that's not a unit vector, right? So your job was to use u vector divided by u magnitude of u so that you can find the unit vector u hat. That was a lot of u's, right? So u hat worked out to be 3 over 5, it's not a 5, 4 over 5, because 5, magnitude was 5, 3, 4, 5 times. Anything else? So directional derivative, tangent plane, right? You have the formula, the normal vector of the tangent plane, the ABC vector of the normal plane was the partial derivatives computed at the point, right? So you have fx computed, fy, and at the point of interest. So tangent plane, you are 100% guaranteed to have a tangent plane. Min-max saddle point, so make sure that you know the formula for the derivative. And then please remember the rules, right? If the d is larger than 0, right, you have those rules. D larger than 0, d less than 0 is saddle, right? So you have those 3 rules, min, max, and saddle. Both min and max at d larger than 0, and then fx either larger or greater than, smaller or greater than 0. fxx.
fxx is, you can switch it out with fyy as
Yes.
well.
So if fxx is greater than 0, it's a
Why can we switch? If it's a maximum point, it's maximum point going this way and maximum point going that way, right? Because it's the top of the
And the only
hill.
time that wouldn't happen is if it was a saddle.
In one direction.
Yeah, d would be.
But d is negative, so you don't have to worry about the x and dy.
It's gotta be someone's.
Someone.
Can we just do an example of Lagrange?
Example of
Yeah,
Lagrange.
just-
Now the interesting thing is the choice of words you had afterwards. Said, can we do an example of Lagrange real quick? The answer to that is no.
Never.
We can do the Lagrange, but it's not going to be really quick.
Don't forget to post this online.
Oh, trust me. Get my eyes scratched out.
She's on it.
Yes. Lagrange. Let's see. Maximum area rectangle in an ellipse. That sounds cool. Max ellipse is given by 4x squared plus 16y squared is equal to 16. Well, that's your constraint. That's the ellipse. So that's immediately your gxy right there. Now, what I need to do is I need to draw these things so I know what equations to use, right? So here is what I'm going to do. I'm going to divide everywhere by 16, and then I have x squared over 4 plus y squared equals to 1. So this means that my radius A, which is left and right, is 2, and radius B, which is up and down, is 1. And that helps me graph my ellipse. So left and right is 2, so 1, 2. left and right is 2, so negative 2, and up and down is 1. And then I draw the ellipse through these. Terrible. So this is the ellipse that we have in our problem. And now I need to draw a rectangle. Now, I don't know where this rectangle is. What I can do is I can just draw a random rectangle. And realize that this point here is point xy. Now that's very important because that makes this distance here distance x, which means that my entire rectangle is 2x. And it makes this distance here y, which means my entire height is 2y. So just by placing that one point there, I know that from origin to that value x is x, but I have another x on the other side, so the distance for the rectangle is 2x. Now I need that because I need the area equation, right? So what's my area equation? Area equation is 2x times 2y. So it's 4xy, and that's your f, because you are maximizing that, right? That's what you want to maximize. That's your objective equation. So we took this word problem and finally transformed it into fxy is equal to 4xy and gxy is equal to the equation we have. Now I can use the simpler form over here. Multiply everything by 4, so it's x squared plus 4y squared equals to 4. We can use the simpler version. It's okay. Great. So that's an ellipse. And this is the rectangle. So now we calculate del f equals lambda del g. So del f partial of x is 4y, and then partial of y is 4x, equals to lambda. And then I have another vector which is del g. Partial of x is 2x, and partial of y is 8y. So now I have orange equation, which is 4y equals 2 lambda x, and I have a blue equation which says that the 4x is equal to 8 lambda y, and I have a purple equation of x squared plus 4. I just noticed that guys, I can't write this. This is not written properly. I have to write minus 4 equal to 0, because g of xy is not equal to 4. So I did this poorly. This needs to say minus 4 equal to 0. There we go. Much better. All right, I have my 3 equations over here. 3 equations, 3 unknown values. Simplify whatever you can. Cancel by 2 on top. It's 2y equal lambda x. Cancel by 4 on the bottom. X equals 2 lambda y. And we have x squared plus 4y squared equals to 4. As we know, these are non-linear systems, and the method to do this is good luck, right? Now, what I see is I see a 2y and I see a 2y. So I can replace those, and Do I actually get anything? No. No, I'm not gonna get anything from there.
You need to put it into the third equation. 'Cause that's the only one that's got multiple terms.
Yeah. So from the first equation, I can get that y is equal to lambda x over 2. From the second equation, I have that x is equal to lambda y. And now we plug everything in the third equation and try to get everything to be in terms of lambda and calculate lambda first. I don't like that. How about if we, well, this is where the fun is, you figuring this thing out.
If you did what you started doing, the 2y equals, you'd end up with 2y equals x squared. Like if you solve for y in the second equation.
So plug in here, we get x equals 2y is replaced by lambda x, and it's time lambda.
If you do the opposite way, you would cancel lambdas.
What do you mean opposite way?
Plug in for y.
If you
Or
say
plug in for
2y
x.
equals
Oh,
x
yeah.
over lambda,
2y equal,
or I don't know if you're doing the algorithm right.
If you do x over, or y is equal to x over 2 lambda.
Yeah.
Oh wait, no, never
Something
mind.
like that.
No, because you multiply either side, you get a lambda squared one.
yeah, you get the lambda squared either way. How about if I solve for lambda?
Can't you do?
That's 2y over x.
Right, and then you plug in an x.
You'd end up
Because we know that, well, we know that x's and y's in this case can't be zeros because you don't have a rectangle, right?
Oh, true, and then you just get y squared.
So plug this in here now. So x is equal to, so feed this in there to get
x squared.
x equals, and then I have 2y, and instead of lambda, I have 2y over x. So that means that x squared is equal to 4y squared.
Oh, yeah, that helps.
Beautiful. And now you take that and you plug in here. So 4y squared plus 4y squared equals to 4. That's 2y squared equals to 1. And finally, y is equal to plus minus root 2 over 2.
Oh, that was fun.
Great. So I have y's, and then I can just replace them back into the equation to come up with x's. So bringing back to this equation, let's say, well, actually, from this equation we can say that y squared is equal to, I need this, but I can also say that y squared is equal to a half, and you feed that there. That's much better version than figuring out. So what we get is x squared is equal to 4 times 1/2. So x squared equals to 2, x equals to plus minus root 2, and there they are.
Isn't that 4 separate points that you get?
Don't you have 4 points?
It was a rectangle.
Oh, shit.
Right? You have
You
4
got so
points.
distracted from the original word problem at this point.
So we have root 2 over 2, root 2, negative root 2 over 2, negative root 2. I'm not doing these in the way they're organized there. And root 2 over 2. And negative root 2, negative root 2 over 2. And there are the 4 points. Those are the 4 corners. So what is the across, right? So 2 times x, it's going to be 2 root 2 times 2 times root 2 over 2, which is 2 root 2 times root 2, which is 4. So the largest rectangle you can inscribe has the area of 4. Which is really cool.
We just follow up for a minute.
Yeah.
So above
But like you have to know
Sure.
before.
Or the solving the craziness.
It really isn't that much. It's just a system equation.
Yeah. It's just like plugging in and solving it. In that, like, in literally.
Third equation
you have like three variables.
the constraint. So in this case, it's ellipse, but I cancel it as much as possible, so I will have to deal with the high coefficient.
Yeah.
So that's your G. So
To equations to define that.
if you up to this equation, all equations that have lambda are coming from the del G equals del F lambda del G, and then you always need an extra equation, which is always constraint.
Because I feel like they don't get good practice.
Any other questions, concerns?
Yeah.
Yes.
I just know you mom. I said I would do that when I remember when I was like, oh yeah, I had this before. And I brought my notes on the train to say
Not too
first
sure
exam,
how
and I did literally that.
to choose a,
Like I literally did like 2 sections of notes. Just like read that and I was like, I'm done. I was on the train for like 2 hours.
Well, the point has to be the one that is close to the one that you want.
Like if I have like
so if you had this say you wanted to approximate sine of x
I'll get at
plus
least one.
cosine of y.
Okay, let's see. So the question is on linear approximation, and we want to take a look at z equals,
It's wrong, right?
what do you got?
Like cosine of x plus sine of y
Cosine of x plus
Oh, yeah.
sine
Yeah.
of y.
at 0, comma
Because remember
pi,
right now.
or maybe 0, comma pi over 2.
0 pi over 2. Well, these are exact values, so we will not be approximating in this. This you can compute. You might be looking at, let's say, 0.1 and 1.5.
There was a lab question that was basically that it might have been like cosine of, I think it was cosine of
Like,
2x
I
and
have to
sine
do it for the first
of
one.
y or something like that.
Yeah, but that's, see, the trick is that they say compute cosine of 0.1 plus sine of 1.5. Let's say that's that. So in this case, you will come up with your function fxy to be cosine x plus sine y. The point of interest would be 0.1, 1.5, but you would be using the point 0 and pi over 2 because that's the nice point that you can compute without. You will find the tangent plane for this function, and to find the tangent plane you would have to use that fx formula. Yes,
So we got something on the lab here called the Laplace equation.
Laplace, yeah.
Laplace, that is not going to be on the test, correct?
No, that's the stuff that from partial differential equation, you research that equation. You are supposed to check the solution. You're not supposed to solve that.
We learned that in the next class we take.
So Laplace equation is simply the second derivative, second partial derivative. So it's not an issue. You have the solution. You're supposed to differentiate and plug in.
I'm still unclear on this. So like this is directly from the lab, and
So this would be this. So I'm just going to cross this out. So this would be the question.
well, can I just give you the question? It gives you a sine and a cosine, sine of x and cosine of y, and it says approximate, or get the linear approximation at 0, comma 2, or pi over 2. So you would have
Yeah.
to
So
choose
they
a
want.
value.
Yeah, but they want you. No. They are not interested in computing anything. They just want you to compute the tangent plane. And you say, I would be approximating in this plane. That's
You
the.
don't follow.
Yeah, they did not spell that. These labs are ancient. So they only want you to find. They want you to find the plane, but they did not they did not ask you to compute anything with it. So what I did over here is I said, well, how about if I ask you to compute something, and then you will be picking this point because this point is close to those decimals, right?
So it would be what, f prime, or it would be the partial derivative with respect to x times x minus
0.
1 or something.
No, it will be x minus 0 to find the tangent plane. And then you would
Then
plug
you
into
add-
x, you will plug 0. Yeah. Well, let's
Unclear with this.
let's do it. That's the
I'm confused about what the lab is asking about.
the lab is asking you only to find the equation of the tangent plane. That's the only thing they're asking for.
It's not, well, it's saying find the linear approximation
Yes.
of the function at the given point.
The tangent plane is linear approximation. They're not asking you to compute they're not asking you to compute a value of any kind. That's the well, the only thing that you're missing there is a wording, because when you say, if you say linearize a function
Right, you get the derivative and
at the point
tangent. Right.
and its tangent, so you providing the equation of the tangent line is your linearization. Then if I want to find the point, you can compute the point in the tangent line. In Calculus 3, if I ask you to linearize something, you will give me the tangent plane equation. And then if I ask you to compute, you will compute the point in the tangent plane. So it's like a two-step procedure. The first procedure is just obtaining the plane. And that's what the lab is asking you to do, just to find the plane. It's not asking you to compute anything in the plane. So,
How do you find a plane?
I don't get it.
How do you find a plane to that?
well, we're going to find the plane here because you have that your the L of xy is equal to fx x minus a plus fy y minus b plus f of ab.
That's the plane equation?
This is the equation of the plane, yes.
Oh, okay.
So now you plug everything in. L of xy is equal to partial derivative in respect to x is just going to be negative sine x, and we're going to compute that at 0. And then you have x minus 0 plus partial derivative in respect to y is cosine y, and I don't like this. I need to switch this
Yeah, it's all 0.
because we're gonna get all zeros. Yeah, so I'm gonna do pi over 2 0, pi over 2 0, and then over here I'm gonna switch this to 1.5 and 0.1. That's what I'm eventually want to get. So this is gonna be then pi over 2, and it's gonna be pi over 2, and then a cosine of y, and then I'm going to have x minus 0 right there, and then plus function computed at these, well, that's going to be cosine of pi over 2 plus sine of 0, so those are going to die anyway. So now L of xy is going to be pi over 2, so that's negative 1 times x minus pi over 2 plus for cosine of y, I'm using 0, so that's also 1. And then x minus 0 is just x. And then plus 0 and then plus 0. So my plane, in this case, Lxy, is equal to negative x plus pi over 2. Well, holy nightmare, this is a terrible problem. L of xy, I just got pi over 2. So it's terrible. I just got pi over 2 because x is cancelled as well. This is why, you know, we need to work on actual problems rather than making stuff up. Let's do the problem from the, pick a problem from textbook for linearization rather than messing with this. So let's go for the book linearization. When they ask you to linearize, your job is just to find the tangent plane, which is what the book wants. there is a second part that you can add to the problem, and that is computing some value in that tangent plane. So let's see what linear approximation. I'm not sure if we did this one. Problem 35 in 15 point, no. This is 14 point something, right? 15.6.
43.
You said problem 43?
That's the one we did in class.
Oh, okay.
No, actually, I don't think we did any. We did 37. 37 and 40.
Oh, we did 37. Okay, so I'm gonna do 35 now. This is 15.6, right? So fxy, instead of being the trig, once you have is negative x squared plus 2y squared. And if this is the only thing that is given to me, and the point at which they want the tangent line, we can just compute that, and we're done. But they want us to estimate how much is f of 3.1 comma negative 1.04. So this is telling me that I should use 0.3 negative 1 to find the tangent plane. So I need to center my tangent plane at this point. So now I have my Lxy to be the fx, which is negative 2x, times x minus a. This should be a as well. Damn it. Plus f of b, which is 4y, y minus b, and this is also going to be bb, and then plus f of ab, which is f of 3 negative 1. Plug everything in. Negative 2 times a is 3, x minus 3, plus 4, y is negative 1, y plus 1, and at the end plus function computed at these numbers. So that's negative 9 plus 2 times negative 1 squared, which is 1. Negative 6, x minus 3, minus 4, y plus 1, and then we have minus 7. Distribute everything. This is still my Lxy. That's negative 6x plus 18. Minus 4y minus 4 minus 7, and Lxy is negative 6x minus 4y, and then minus plus 7. This over here, this is technically a z, so this over here is the tangent plane. So this is the tangent plane at 3 negative 1. So now I claim that f of xy is approximately the same as L of xy. That's the claim. So now f of the numbers that they want, which are 3.1 comma negative 1.04, is going to be the same, the close to calculating L at 3.1 negative 1.04. So I used 3 negative 1 because those were easy to find the tangent plane. Once I have the tangent plane, I'm going to use the original values they gave me to compute the z, which would be very close to the z that is actual true z. So I have negative 6 times 3.1 minus 4 times negative 1.04 and then plus 7. So that's equal to negative 18.6 plus 4.16 plus 7. So that's negative 7.44.
Sort of lost me when we switched to x's from x's and y's to a's and b's.
Okay, so this is the AB, and this is the close point. And you find the close point, then it needs to be close to the point that you actually want to compute. So in Calculus 1, when I want to compute the square root of 80, right? I would consider A to be 81 because I can actually take a square root of 81. So now,
Close.
yeah, right. So now I have 3.1 and negative 1.04. The close point is 3 and minus 1. That's something that I can easily calculate here. So when I find my fx derivative, I have to compute that derivative at a and b. So it replaces the full notation for the formula is L of xy is equal to partial derivative of x computed at ab times x minus a plus the partial derivative of y computed at this easy point, right? Because the goal is to compute that easy point to find the tangent plane. So that's why I'm computing my fx and fy at a and b, which are the easy points. So this is the tangent line formula, tangent plane formula, and I am going to take the partial derivative in respect to x, but I'm going to compute it at a and b because a and b are the easy numbers that make computation easy. Because this is approximating, it's not giving us exact. And then we have x minus a. And then I have partial derivative here again, computing at the easy point. So a and b is the easy point that you pick that's close, and then you calculate the tangent line at that point. And then you actually use the original point. Once you simplify your entire linear line, once you simplify it, then you use the original point inside the linearization and you compute the value. So again, this is something that we don't use today in the field at all because we have computers to compute these things like that. And in good old times, we actually had to compute all of these values by hand, so it was easier to pull this off then. Plus, there was no calculator for square root of 80, so you had to use linearization to get the derivative at the easy point. This is a and b, also easy point. You are computing a function at the easy point because the purpose of the linearization is to replace the annoying point with the easy point to make the calculations easy. And it happened to approximate it very well because it's a tangent plane. You see, if I want to calculate this point here, but this is the easy one to compute, I'm going to find the tangent line for that point, and you see that the other point is very close. That's the purpose of doing it, right? So if I don't know what the annoying point is, but I do know this point, which is the easy one, I find the tangent plane at the easy point because those calculations are a joke. And now, when I put the tangent plane on it, when you look at the other point, the z value of the other point is very close to what the z value is if you calculate the tangent plane. So that's the purpose of linearization. Better?
Yeah, that's a little clearer. Last question is the lecture on 16.1 is, I don't know, I can't find it. The one that was last night.
What was the last time?
16.1. Did we get a lecture last night? I left early, I think.
Oh,
Because
yes,
you told me to.
I did not post because it's not going to be on the test. So I'm
Right.
going to post those lecture notes. I did not post anything from chapter 16. I did post, was the stream okay last night or no?
I didn't have any yet.
No, I mean,
I couldn't find it. I just checked right now, or an hour ago. This one was good. Tonight we got, but last
but
night.
there was no stream for 16.1. Probably died. That's the issue. I don't see when the stream dies. I don't know. That's why I always ask for one student to watch the stream in the class as the class is going, so they can tell me, hey, stream died. Because I know for a fact that my stream died twice in Calc 1 so far, but I do not recall stream dying ever or being reported for you. But you will.
I can find a note. Another semester's 16.1 stream.
Well, it's this book renumbered
Yeah.
the chapters,
I know.
so you will be looking for 13.1.
Yeah. Okay.
So on my stream, look for 13.1. It's the same concept, it's just different number. So put the note in your notes if there is no stream, and then please tell the rest. If there is no 16.1 video, they should be looking for 13.1 from older. You're going to have at least 5 13.1 lectures, different lectures, on my channel, for maybe even more. I didn't delete any of the lectures in the last 5 years, I think. It's like
Yeah, so there's
1,200 videos.
There's one playlist for Calc3 in 2017, and I saw it there.
Yeah.
One last question about
Yes.
projects. Like the instructions, it says you have to do all 4, but this one's labeled as an honors option.
The 3.
So all 3,
Yeah,
you
3
get.
good. Yeah, 3 is honors option is for if we are running the honors section. I mean, you are welcome to to do it if you want to. All right. Anything else?
The min-max saddle, it's just that equation.
Yes,
Three.
the second derivative test.
Okay, there's 3.
Again, we're looking for something that's a little bit, faster to compute. We're not looking for.
Lagrange, just that equation. You said there's not going to be a 3-variable Lagrange, or a.
If it is a 3-variable Lagrange, then you will be getting something immediately. So, yeah. Or it's symmetric. So.
Oh yeah, computing level curves. That was way back in the beginning. Of
Yeah,
the
it's just
chapter.
you have equation z equals to some blah,
Okay.
and then the level curve at z equals 1 is you replace that z in the equation with 1, and you get some curve. What do you get?
You just
right.
solve it. Like,
Well, you don't get a number, you get an equation, right? You get a 2D equation. See, if I have, let's say, I have a watermelon, right? And I set that watermelon on a tabletop. And I say, my z now is 0. That's z equals 0 is a floor, is a countertop. So if z equals 0 is countertop, it's going to cut below the watermelon, and all you're going to have is 1 point, right? Okay. And then if I say 1 inch up, then z is equal to 1. And you will plug that in the equation, and you will eliminate z because z became 1. And when you work out the algebra to add all the
you would find
numbers, you will get x squared over something plus y squared over something equals to a number. And that's actually the equation of the ellipse to the equation of the ellipse, because if you came in with a sword 1 inch above the, right, and cut through the watermelon, the outline of the watermelon where you cut would be that equation of the
So you're
ellipse.
looking for an equation now.
You are looking for the equation because you're looking for level curve, right? When you're looking for the derivative, you are looking for the value because that's the value of the slope.
Now, is that like the curves? That's like the map thing that shows you
Yes.
Okay.
Because you're cutting the slices.
Right.
And the equals z equals 0, z equals 1, z equals 2, z equals 3, z equals 4. And each one of them produces an equation.
That's good. That slope's matching the shape to the equation. That's just like the ellipse.
Ellipsoid, paraboloid, and all of those cool, those 6 shapes.
So I have to write.
Come on, one is a cone, and one is a saddle with a hyperbolic paraboloid. Ellipsoid is a watermelon, ellipse either way. So you technically just need to learn hyperboloid of 1 and 2 sheets. And elliptical paraboloid is the umbrella.
I know what it looks like, but how do you? I know what it looks like, but how do you write that in an equation? Look it up.
Because if I tell you now, it comes through this ear and it goes through the other ear.
You're surprised. Yeah, but when I pay attention, it usually sticks in there pretty good.
So,
But I think it's
Yeah.
good. So I'll just look at that real quick.
good.
I can't imagine there's more than one, maybe 2 questions on that.
Multiple choice?
Yeah.
Yeah, give you an equation, give you shapes, match the shape to equation, match the equation to shape.
And then
Takes 2 seconds.
limits, you basically just plug and try to see what's going on there. Okay. Continuity, the rules are the same, right, from Calculus. Alright, that's it. That's all my questions.
All right.
Yeah.
Hasta mañana.